Good afternoon, all. Uh, Good afternoon to all the panelists and the participants who are viewing this. We are to our session two, which is flexible operation in power plants. Mr. Prabir Kumar Majumdar will be the session chair for this. Over to you, Prabir, sir. We can start the session.
This is. Can you hear me?
Yes, sir.
Are you-
Yes, sir.
Great. So I will start the session. Welcome.
Yes, sir. Please start the session.
Yeah. Welcome all the participants, delegates, and the panelists for today's session on this power plant summit. Our topic is on flexible operation for thermal power plants. We have three panelists who will be talking on this flexible operation. Mr. Dr. Oliver Then, who is the executive MD of VGB Powertech. He will be the first speaker, and then followed by Mr. Sandeep Chitora, who is the head of MindSphere Siemens Application Center. And then the third speaker would be Mr. S. Banerjee, who is from NTPC as AGM NTPC. So we'll start with the first speaker, who will be talking on flexible operation, achieving technical minimum in thermal power plant. So before he starts, I will just set the tone of this session. You all know that today in India, we have continuously adding the renewable source of power generation. We have about of the total, the installed capacity of 370 odd gigawatts of total power capacity. So which is almost a 25% or 23, 24% kind of, the composition. And we are poised, add further in the next 10 years, which would be around 435 gigawatt by the end of 2030. So this is going to be a huge addition, and the other sources, thermal and hydro and nuclear, etc. This is quite a big jump because the total installed capacity planned up to 2030 is 830 megawatt odd, gigawatt odd. So you can see that the composition of renewable is going to continuously increase from the level of today 23-24% to almost crossing 50% in the total, the power capacity. And you all know that today thermal power plants are the backbone of our power system, and wherein today whenever there is a and we are giving priority to that, and as a whole, the for the environmental reasons, we are poised to grow on the renewable power. And advent of renewable power in the grid has put us on a lot of challenges. There are technical challenges which are turning into a commercial challenge as well. I will quickly name some of the technical challenges. Like we have the decreased efficiency at lower load, then which result into higher fuel cost, and then we have the problem of maintaining optimum boiler chemistry or the system chemistry as well. And then we also have at the lower load potential problem of catalyst fouling the NOx control system or the equipment. Then we have high increased of human error when we operate at the low level of in the thermal units. Then we also have the mixture of machines or the units of different ages. Some of the equipments are or the units are of the older era, whereas many of the plants are of the newer era, where we talked about supercritical and ultra supercritical power plants. So their capabilities are different. So there is no one formula for everything. And then also there is, whenever there is a such kind of variations, then you also have the thermal fatigue and the damage of the equipment, etc. So these are the technical issues, and ultimately the commercial issues come up as a resultant of this technical issue. Our cost of startup goes up, our APC, O&M cost, R&M expenses, everything will go up. Then heat rate, there would be a degradation. And then of course, there would be overall cost of generation, which will get affected. And ultimately this result in this competitive market, there would be the challenges faced by each of the generator. So, so let us cut it short now, and let us listen from our the esteemed the speakers on the panel. So I will invite Dr. Oliver Then, who is the Executive MD of VGB Powertech. VGB Powertech, I think he can introduce quickly on what is VGB is doing. So over to you, sir, Dr. Oliver Then.
Yeah, thank you, Mr. Mayumdar, for this kind introduction. You have taken already some slides out of my presentation, but I think it will be an interesting session. I'm very happy to be invited and to give a contribution to this Indian Power Plant Summit today from Germany. And I will start with some overarching issues leading to flexibility and flexibility requirements, and highlight some first technical issues before I then come to my fellow presenters, which have much more and much deeper knowledge on the technical issues of flexibilization. So this session fits perfectly together, and I'm about to start now, and I just have to share my screen with you, and I hope it works. So if you can see the slides, I would be very happy. Maybe you can just give me a sign if the slides are visible on the screen.
Yes, it's visible.
Yes,
that's fine. That's fine. So flexible operation, and I will start with what about flexibility? Why are we talking about flexibility? What is the benefit and the value, and also the future value of flexibility? And what have we done so far? And how can we further contribute to the development of the Indian power sector? And as Mr. Mayumdar said, I will quickly introduce VGB. VGB has been for 100 years now the technical association for the power plant operators. And nowadays, as we also go to significant changes, the technical association for the operators of heating plants, of energy storage plants, and of course, in the new future energy system, of operators of power to X plants and these kind of facilities. We have international members, as you see on this map of the world. Unfortunately, to be honest, you see that the Indian continent is not highlighted so far, but nevertheless, despite missing members, we are nevertheless, since years, working in India, and working together via the German Ministry for Economics on the Indo-German Energy Forum, and in partnerships with a lot of Indian partners and stakeholders. And I just try to move on here. Okay, and you see just at a glance, I don't want to run through it. So it's since more than 10 years that we are active in the Indian power sector, which fills us with pride and which has been a very interesting and a very successful time, mainly in the last years working on the issue of flexibility, and nowadays still working on flexibility, moving also into the issue of hydrogen, which has been mentioned by the American colleague in session 1, hydrogen and power to X technologies being the logical continuation of power generation in the future. And I will give a short update on our recent activities further on. And now what about coming back to flexibility? Why are we talking about it? Well, this is a very rough overview about how the future electricity supply will be derived of, or how it will be composed. And as Mr. Majumdar said, variable generation coming from wind and solar PV will be definitely one of the major pillars of future electricity supply, amongst other renewables, amongst nuclear, and at least in certain countries, and in spite of a still existing share of fossil-fueled power plants based on hard coal, lignite, and gas, but with decreasing tendency, because the major part of all investments into the power sector is definitely going into renewables, as it is the case in India with the very ambitious goals that the Indian government has set, and together with the ambitious goals that have been set here in Germany and Europe by the European Commission. Then we will still have the second pillar, which is dispatchable generation. Because as variable or generation from wind and PV is volatile, we need flexibility options in the system. We need flexibility options, and we need capacity to fill the residual load requirements also in the future. And thermal power plants are at the moment, and will be at least for the next decades, still the major provider of flexibility in any kind of energy system, at least on a global scale. It will be added up, and it will be replaced step by step by means of energy storage. And this means the full scope of energy storage options, from the classical ones up to the future ones like thermal storage, which might not be that interesting in India, but the power to X technology, so power to gas, power to hydrogen, which also offers what we call sector coupling, which is using electricity in other sectors, electrification of the society and industry to decarbonize. And if this is based on wind and PV with increasing shares, also the demand for flexibility in the system is increasing. And this is a snapshot from this year's July in Germany. What you see here is power generation in the different colors, which I come later to. And in red, you see the demand curve. And you see in yellow, of course, PV. And you see we had a very sunny July this year. We had wind, very volatile, wind in dark blue and light blue, which is onshore and offshore. And at the bottom, we have the, let's say, baseload renewable generation coming from biomass and hydro. And the gray area, this is the one which is needed and which we call the residual load. And you see the high fluctuations also lead to very high fluctuations in the gray area. And this gray area has to be covered by conventional plants and nuclear plants and import-export, mainly in the end to fill up the red demand curve. And you see it's a daily, it's a weekly fluctuation. We have times where the contribution is very low in the middle. We have times where renewables could theoretically fulfill nearly the complete demand. And this has to be covered. But flexibility has even a wider approach. It goes down. It goes down from day to the hour, to the minute, to the second, to the millisecond. And in the other direction, it goes from week to months and from months to season. So the requirements for flexibility are a very heterogeneous and complex environment. Now, if you look at the same July here, and what does this mean now? If we look at the gray area, what does it mean for the conventional plants or the fossil-fired plants? And you see here in brown, lignite plants, in black, hardly visible hard coal, and in gray-blue, natural gas plants. And you see two messages at least in this chart. So they are flexible because they are following the fluctuations in residual load demand very, very exactly. And this goes down to the minute and to the second. You see that gas, although the share of installed capacity is lower than the share of installed capacity of hard coal plants, gas has taken over a large portion of hard coal role and hard coal generation due to the economic environment, increased CO2 prices, etc. And you see that lignite is still not going that ramp rates up and down and to that minimum load compared to what we see in the hard coal and the natural gas area. So you see very complex requirements on all sorts of thermal power plants, and we have skipped here biomass. And now what are the major requirements now if you look to the single plants which in the end form up these curves for the fossil-fired fleet in Germany? And this is shown here on this chart. You see what are the main elements of flexibility for this dispatchable generation that we have. And the first column on the left side is coming from the title of this presentation, is of course about minimum load operation. Low minimum load is one of the key figures for any fossil-fired plant in this flexible environment, because it allows fast start up and meeting the requirements, and also being able to stay on the grid when there is a high injection of renewables into the market, because staying at the grid at low minimum load is in most cases much more economic than shutting down the whole plant. And we are not talking only about the startup costs that come again and again if you have to shut down completely. We are also talking about the possibility to continue to provide system services when you are in minimum load. So if you're talking about voltage control or frequency control, these system services, of course, can only be provided if the unit is still connected to the grid. The second one, advanced dynamics by high ramp rates for shutting down, for increasing and decreasing the load, is of course very important. And we have seen very impressive figures in session 1 of this event here, coming from the advanced ultra supercritical plants, which have now been commissioned in India. And it's a challenge for the existing plants to increase ramp rates, to follow the market and to follow the demand and requirements. And last but not least, of course, we are talking about startup and shutdown times. So if you have to shut down, of course, it's very important that you are able to return to the market, return to the grid as quickly and as efficient and cheap, of course, as possible to follow even 2 shifting regimes for hard coal plants, which we have seen here in Germany. And the different technical measures where we end up in our projects, they can address also not only a single element of this flexibility portfolio, but they can also contribute to more targets. And unfortunately, sometimes they are contradicting. So increasing the flexibility of a plant is a very heterogeneous task, is a very complex task. And I think my fellow speakers will highlight these issues. It's a tricky kind of animal, as we say here. And sometimes you have clearly to make your priorities to address the right flexibility parameter depending on the market you are actually working in. What are the flexibility parameters that can be achieved by thermal power plants? And we are constantly updating this table here. And we have given the figures for hard coal, lignite, and CCGT as a classical fossil fueled power plants. And it looks complex because you see 3 figures in each cell, but in the end, it's quite easy. If you look at hard coal plants and the ramp rate, you find 3 figures here. Ramp rate in percent of maximum load per minute. And you see 2% is something that comes from a very conservative approach. It might be the average of an existing fleet with a lot of older plants. In the middle, the 4% per minute stand for what can be achievable with state-of-the-art power plants. So if you buy a new plant, you should at least achieve the figure in the middle, the 4%. And the 9% is for very advanced optimization, or which we see as being possible in the future. So 9% for a hardcore power plant seems to be very, very advanced. Of course, it cannot be achieved in all plants, and retrofitting existing plants might not lead to this very advanced figure. But nevertheless, what we have seen, and I show the figures, something between, for example, 4 to 8% for an existing hard coal power station is doable and is accessible. So this is more before I go through all these figures. So this is more to read only, but there is still room. So we have achieved a lot, so to say, in the fossil fueled power plant world, and there is still room for improvement in the past. So how can we move from left to right in these figures? And these are just the keywords, and I think my fellow speakers will go into some more details in the following presentations. The first thing what we have learned.
2 more minutes.
2 more minutes.
So you have 2 more minutes. Please
okay.
Hurry
Thank
up
you.
that.
Yeah. It's a general optimization of instrumentation and control. So high level of automation is in any case beneficial for any kind of flexibility improvement. It's about precise steam temperature control. It's about coal supply, about drum level measurement. It's about automated operation and switchover of pumps, fans, etc. And the inclusion of feed-forward control. So this high level of automation is beneficial. It's crucial, and it's sometimes even quite easy to achieve with less investment. Combustion optimization is a second part, mainly composing of the air and fuel coordination by advanced mill operation or advanced monitoring of the combustion parameters, which sometimes need a little bit more investment. And of course, you have advanced measures like changing the operational regime, including new means for frequency and power control, or even the inclusion of internal thermal storages. So these are some figures or some measures that can be implemented here. We have provided a flexibility toolbox, which you find on our flexibility landing page. And under this URL in the internet, you can find this and a lot of other information for download for free. And I can really guide you to this site, to our flexibility landing page, and you find an overview about all potential measures that can be implemented to achieve higher flexibilities. And just as a last slide, the outlook, we have done successful projects, for example, at the Dadri power station together with NTPC in a project sponsored by the Indo-German Energy Forum. And we have achieved very good results regarding minimum load and ramping tests, as you can see here. And the project was so successful that we are now continuing this in a follow-up project under the Indo-German Energy Forum for further tests and optimizations at the Andal power station operated by DVC and the Maiton unit operated by Tata Power. So to spread out the results and the learnings also into the IPP sector. And of course, we hope to continue this to all interested power plant operators in India to give our contribution to the further development of this sector in India and to allow you more inclusion of renewable energies in the future. In terms you have any questions, please feel free to contact me, for example, here with any kind of question, and we would be happy to provide you with more information. And I would also like to address our partner organization in India, which is the EEC, Efficiency Enhancement Center for the Indian Power Sector, which is in cooperation with us coordinating these projects and taking care of the dissemination of any kind of results out of our experiences in India. So thank you very much for your interest, and I'm open for questions later on. Thank you.
Right. Thank you, Dr. Oliver, for it. Now I will invite Mr. Chia, who is from Siemens Application Center, who is also heading the MindSphere, which is a IoT-based solution for this flexible operation. So please, Sandeep, please, you can carry.
Thank you very much, sir. Good afternoon, everyone. I will start and just share my presentation.
All the participants are to put their question on the chat box.
Hope my screen is visible.
Yeah, it's visible. You can display it.
So scenario in India, like currently what we are operating is close to 370 gigawatt is what our installed capacity is, and in that we have 206 gigawatt of thermal power plants. What we see is a typical scenario. What we will see in 2022 would be, as projected by CEA, is that we will require close to 180 gigawatt of generation during the entire day, or close to that. Thermal-based generation will be 130 gigawatt. But as soon as solar starts coming up or picking up from morning to peak noon, we need to lower our thermal capacity in order to balance the grid. And this 130 gigawatt is expected to go down to close to 45 gigawatt, which will require sort of ramp rates of thermal-based generation is around 200 megawatt per minute. And then as soon as solar goes off during the evening, we will also start have to pick up the load from the thermal-based generation. And this capacity or this ramp rate would be around 220 megawatt per minute. So what we see is close to 70 gigawatt of drop coming during the morning time, and about 100 gigawatt of pickup required during the evening time. Another scenario we are seeing, the PLF of the coal-based power plant is consistently decreasing. Like if we see from 2012 onwards and up to 2020, we are currently operating, or most of our coal-based power plant are operating at around 56% PLF. Gas is almost stable at very low PLF of around 20, and in some cases even lower. What we also see is from solar and wind, we see a stable PLF of around 23% and around 20%. So like solar will start picking up slightly with the renewable integration and with the technologies that are coming up from the thermal sector as well. What is happening because of this cyclic thing is that the forced outages based on the number of starts are increasing, and this is a study that is what has been done by VGP. That if we have the number of starts increasing, then the number of forced outages also increases in the same relation. So we see a direct correlation between number of starts of the machines with forced outages. On the second graph, what we see is that the equivalent full load hours, which means like if my units are operating almost at the 100% load, and if the equivalent full load hours is 50%, so it's basically saying that the PLF is 50% on an average basis. So we see if the equivalent full load hours are decreasing, which means PLF is decreasing, we also see the number of forced outages is also increasing. So it's an inverse relation between the equivalent full load hours and forced outages. So what we have observed is also on the thick wall components, especially that the crack that get initiated in these thick wall components are getting started appearing, and this is what we need to address. We need to have the reliable operation in order to bring these coal-based power plant to a lower load, and then also participate in the renewable integration in the grid. So my thoughts are like even a dead clock shows the right time twice a day, and so we have quite well operated and managed power plants. So I think we shall be able to do much more or much better than what we see as the scenario would be, that the PLF is started dropping heavily, and then there is also a renewable coming in. But then coal will also have to play an important role in this renewable integration. This is what my thinking is, and that is what I will elaborate in my subsequent slide. We have achieved 40% technical minimum, and this is possible. So this we have done together with VGB, which was what my former presenter here, and NTPC, which will be subsequently done. So this as a combined team, we have demonstrated that 40% is possible on the Indian coal condition without oil firing. So nothing to worry about it. And then I think all 500 megawatt units, once we go in step-by-step manner, we will be able to achieve close to 40% technical minimum. What we see on the left-hand side here is the plot that we have taken from the unit load of 500 dropping to 200. And then we have also done an exercise at how shall we tackle any fluctuation that happens in the load. So that is where we see this kind of a bump coming in. And we see that main steam temperature remains more or less constant once we slowly go and achieve the technical minimum load. But reheat temperature is not getting able to maintain, and that causes sort of stresses on the IP component or IP turbine component, reheat side areas. But the advantage of bringing these thermal power plant to the lower load will be that we will be able to save, or let's say mitigate CO2 emissions, which is getting generated by these thermal power plants by augmenting solar. And this is, our estimates are like this will be close to around 100 million tons of CO2. The coal conditions that have been used is like already high ash. Yes, high volatile matter was also present during this time of coal, but we see that we shall also be doing the testing further for other volatile material coal conditions, and we are hopeful that we will be able to do successful demonstration on these as well. So the major thing that an operator can do in order to reduce or improve the thermal the life of the components is two-way, that if he is able to reduce the temperature gradient, which is how much temperature change that is happening on a component from 1 Kelvin to 10 Kelvin per minute. If the number of or if the amount of the temperature gradient starts dropping, then we are able to allow more load cycles on a component, which essentially means the higher life. On other hand, if that comes to us as a designer, that if we are able to design the component which is having the temperature gradient across the thickness of that component is as small as possible or as thin as possible. So if we are having lower temperature gradient, then also we are able to allow higher load cycles. So that is how, like, I see that there are two ways in order to achieve the better fatigue in the component, and which I also explain in the slide here, that some of the life is getting consumed because of number of starts. So this is a damage which is happening because of cold start, hot start, and warm start that is happening. But then other thing that is available because of the temperature change, we are consuming this much of the life. And if we say that if we are able to design components which, because of the load changes, are having, let's say, 100 Kelvin of temperature drop, then at this point I will be having, based on the life curve of this any particular component, I'll be hitting the life here, and this is where the crack gets initiated. But if I reduce this temperature gradient from 100 to say 50 Kelvin, the life of the component increases significantly. So that is how, like, we now are designing our components with the smaller thicknesses, so that the component life is increased for the future flexible operations. This is another way wherein, like, we are able to convert any cold start into, let's say, warm start. And what we are doing here is, like, we are providing an electrical jacket on the HP and IP turbines, and as soon as we want to start the unit, we can start this electrical heating, so that the component gets heated up quickly, and we can start the unit faster. The advantage of this will be, once we do a boiler start, we don't have to wait for turbine to, let's say, come up to the temperature and then roll it. In this way, we are able to reduce the startup time as high as like 60 minutes than prior, which means that we are also able to reduce the oil consumption and reduce the cost for the start. And similarly, we will also be able to reduce the number of, let's say, operating hours, or the life of the component will also get improved. So this is how, like, if we see that on this, we will be able to start the machine earlier. This is my conventional cold start, and if I change with this electrical jacket, I'll warm it up faster, and then I can have the standby mode available, so that as soon as the boiler comes in, I'll be able to roll the turbine to load. So this is a faster startup method that we are seeing. Now I'll present a scenario wherein, like, it's an economic case, which I think is beneficial for the grid. So we are assuming that currently the entire optimization, which is on 500 megawatt, is happening because the rated capacity is 500 megawatt, and we see the technical minimum, let's say 50% coming to 250 megawatt. With and modernization of this unit, what we can do is we can improve this 500 megawatt output to 550 megawatt, and also reduce the technical minimum to, let's say, 40% to 200 megawatt. So what happens is, if I am having a unit of A unit, which is at pit head station of 500 megawatt, and unit B, which is off pit, which will see the flexibilization. Current operation that is happening is 500 megawatt here and 300 megawatt here. If I assume a variable cost of 1.3 and 3 rupees, the annual cost of operation comes out to be 1350. So summing together both for the both units. But in proposed operation of 550 megawatt and dropping this 50 megawatt to other unit, our new estimated cost of operation will be 1.25 and 3.05. And based on this, we see that we are able to operate both of the unit, and summing almost 800 megawatt, getting at 1270 crore. So this will give us a saving of 88 crore annually by just optimizing the units together, or putting two units together. This is why I also see that flexibilization along with modernization can provide an economic benefit as well. A concept which we have introduced in our supercritical unit can also get introduced for 500 megawatt and even 210 megawatt for improving the faster ramp up. This is again coming together with the electrical jacket as well. What we are doing here is we are able to reduce the inner casing thickness so that the startup of the unit happens faster. And since they are able to have the faster startup, we save costs. Similarly, they are also given with interstage admission or overload admission, so they provide the better ramp rate requirement. So if we want to improve the load quickly, we are able to introduce with this overload admission and support the grid. In order to monitor what is happening on the steam turbines, we are having EOH 4.0, which will account for all the load changes, all the thermal fatigue that is happening, type of starts that you have taken, and also the actual hours that the unit has got operated. So it will give you a complete operating hours, or meaning like an accurate counting of how much life has got consumed for the component. And based on this, you are able to decide that whether you need to take a shutdown, whether you need to really do the maintenance of the unit or not, or you can prolong your operation. So this is a solution which comes very handy in order to provide the maintenance of the power plant. Now comes up a unique solution, or I would say question comes up, like once we operate a unit in a part load, how do we improve the efficiency? And this unique solution is we are able to introduce a top heater. So this top heater actually operates at part load. And once it operates at part load, we are able to maintain the final feed water temperature constant. And since we operate the final feed water temperature constant, the heat load on the boiler reduces, and that's how like we are able to improve heat rate. This we have demonstrated in plant in China, Waigaochao, which have got commissioned in 2008. And we are seeing the heat rate improvement close to 0.6% at 50% load. So this is the methodology that
Please speed up your presentation. Yes. We have
Sure,
only
sir.
2 minutes of time left.
Sure, sir. So I think it's like mostly already done. So if we see that top heater, if we operate in normal operation, as we go in part load, it starts stopping. But with the use of top heater, we are able to maintain the temperature of final feed water, and that's how like we are able to improve the heat rate of the unit. Condensate throttling. This is another unique feature we have done it in NTPC Dadri, which is able to provide the fast response to the grid by closing the LP extraction. This is a PESEL analysis or PESEL framework that I just want to give a thought as an ending thought of flexible operation as a need for our thermal based generation. First of all, it is political in the sense like it will provide energy security to the country, and that is why we see that it gives us a large potential. It is economical if we combine it with modernization, which will reduce the cost of operation, as an example I have presented today. It is a social also, which means like we can create a lot of job and also for the skill development, because the transition will be smooth. We have proven technology available, and it will get further developed as the requirement comes in. We work in the legal requirement or in the legal framework itself, which is like whatever is the regulatory emission requirements, we are able to meet those. And ecological in the sense like we will be able to reduce the carbon footprint of the country by integrating thermal or by reducing the load on the thermal to integrate renewable in the grid. With this, I end my presentation. I'm available for questions, and anything that comes up to you on, you can always contact me on these flexible operations. Thank you.
Thank you, Sandeep. Very nice presentation. You have left a lot of thoughts which whether you can be connected and maybe, the users can take benefit out of that. Yeah, now I will invite Mr. Snashish Banerjee from NTPC, who will be sharing his experience on flexible operation. Over to you, sir.
Thank you so much. Is it visible slides?
Yes, sir, but you have to make it full screen.
Yeah. Thank you so much, Mr. Mujumdar. And in fact, all three of us, the panelists, are working together unitedly in the mission of successing this particular aspect, the flexibilization challenges in India. In fact, VGB, Siemens, and NTPC together had taken some of the pilot studies, and based on that, we have developed the foundations of moving ahead. Sir, probably you have touched upon these 87 gigawatt of power, renewable energy, and the renewable energy is unpredictable and with the different weather conditions and limited availability of hydro, pump storage, and other gas stations are really forced that there are no other option but to flexibilize the coal units. In fact, the flexibilizations are being recommended to the extent of minimum loading up to 40%. It is visible in different CEA reports that by 2022, when 175,000 megawatt power, renewable power will come into the grid, then we may have to come down up to 40%. And even then, there may be some units which will be under reserve shutdown. As we are witnessing nowadays, either the units are running at full load or units are in stop conditions, in reserve shutdown conditions. Even very high efficient units, the supercritical units are in stop condition. That's because it is located non-pitted areas and its power cost is little bit on higher side, even though it is having a efficiency hit rate to the tune of 2000, 2100. And this is the situations in India nowadays. And the features of flexibilizations, there are multiple facets of flexibilization that I want to touch here. The first of all, the reserve shutdown. Reserve shutdown is also of different types. It can be a very short shutdown, short durations, 1 or 2 days durations. It can be a 7 days duration shutdown, or it can be even months shutdown. Some of our units are shut down for months. So the approach of addressing all those reserve shutdowns are entirely different. The way we should handle for shorter wet layup will be entirely different with the dry layup, what we normally do for the units which are under shutdown for months together. So these are the different aspects of reserve shutdown. Apart from that, there are minimum loading operations, the significant load following, maybe load following very minor load following, 30, 40 megawatt load following, and uh, and all these, in fact, all these different dimensions of flexibilization we are witnessing in NTPC across different fleets. And apart from that, RGMO and the grid response, the methodologies, these are also part of it. I think this is also should be covered in the flexibilization gamut. So all together are the aspects of flexibilizations. And this is the initiative, one of the important initiatives which we have pursued in Dadri, then Mauda, then Vindhyachal. So these are the three pilot studies we have done. The major thrust of the study was the minimum loading operations and with a higher ramp rate to the tune of 3%. As we have seen VGB experience that they are having 4%, even 9% ramp rate. But in Indian conditions, the Indian concept of ramp rate is, I think, is a little bit different. What we perceive the ramp rate is from say technical minimum load 55% to full load 100% in one go. Then only we can tell it is the ramp. So it is not a smaller range load range ramp. It is the very larger load range ramp that we are experiencing, and we are pursuing that. And advanced process control, that is another the flexibilization approach we are taking at Shimadri. So the multiple way we are pursuing, and now we want to touch upon, said you have touched in the your introductory message, that the issues which are really affecting our power station's life, impact on power station equipment through flexibilizations. These are some of the aspects what we want to highlight here: the poor combustions, the compromise in the combustions regime due to improper air-fuel ratio, primary-secondary air ratio. There may be coal pipe choking, improper in balancing in different coal pipes. There may be primary air fan stalling due to low primary air flow at a 40% minimum load. Flue gas temperature exit at air filter can approach the acid dew point, which can come down around 105 degrees centigrade. There are chances of steaming in economizer as we come down at a lower pressure, lower drum pressure, with the saturation temperature. Uh, at that particular case, the economizer steaming can take place. Similarly, low air filter sometimes can lead to situations where the cool drying will be an issue. The cycling loading can lead to thermal fatigue in separated heater outlet headers. So these are some of the aspects, but one thing is sure, that boiler is the worst hit in across all the gamut. The operational aspects, I want to highlight some of the aspects. The high ash deposition on the ducts, the chute blowing is not possible at low load. These are operational problems. The prone to furnace flame disturbance, slipping due to variation in cool quality. When we run the unit at 40% minimum load, we have to run with the 3 mills. With the tripping of a single mill can lead to the tripping of the units. So that sort of uncertainty we are passing on. Similarly, the fluctuation of chemistry parameters, as we have rightly told in the beginning, that is very, very crucial with respect to minimum load operations. And some of the environmental aspects are also there. That is, flue gas temperature falling below acid dew points, and poor combustion can lead to CO formations. Similarly, in the turbine, though it will follow, it will not immediate. The turbine affecting turbine may not be immediate in nature, but the temperature and hot heat, steam temperature fluctuations, the excessive use of exhaust fluid spray in the LP turbine last stage, the wear and tear of the control valves because of severe throttling, low load deposition due to chemistry, poor regime chemistry on turbine. So these are some of the effect on turbine. And this slide is showing down how we come down to minimum loading at unit 6. And in that we were 40% minimum load had achieved. And the last column, the remark column, it is showing that there are some, it is said that it is successfully operated at 40%, but with the rider that there are number of variations in terms of parameters, say steam temperature variation, drum level fluctuation, flue gas temperature coming below acid dew points. So multiple way the parameters deviated, and this is the areas what I want to like to highlight here, the how the different parameters, important parameters can fluctuate, can deviate during this minimum loading and higher ramp rate operation. When we come down, when we operate at a higher ramp rate, our main steam and HRH steam temperature will fluctuate, maybe to the tune of 20 to 30 degrees centigrade. But these fluctuations will lead to issues, as our friends of Siemens have told, that how it can affect the fatigue of the equipment. So temperature fluctuations should is to be minimized, say certain limits, 8 degree, 10 degree, 15 degree, that much can be allowed, even when we are running with a higher ramp rate. So how to minimize that? So interventions in these areas, maybe with some smart temperature controllers, what we are experiencing with the help of Siemens and other OEM to introduce these things, which are little bit smarter. The controllers are smarter. They will act proactively rather than reactively. What is presently in the loop cooling system. So that is the temperature part. And then reheated temperature, it is another area where sometimes it crosses the excursion limits. And again, this smart temperature controller can help us with respect to containing these temperatures. And basically, the advanced process control, what we are introducing at Himadri, and some of the aspects at Dadri, which will really, which can give us some sort of confidence that, okay, with this smart temperature controller, we can go ahead without having deviated these parameters too much. And this is another area that you can very well you can acknowledge that the flame scanner is an area where when we come down at a lower load, it is always coming in your mind, operation mind, that how 6 meals or 7 meals operations, when we come down to 40%, we come down to 3 meals, how the flame scanners will look like and how it is varying, say, in a full load conditions to minimum loading conditions. And again, there are some solutions, worldwide solutions available to address those issues. Some of the solutions I have highlighted here, but one of the major solutions, I think, in these particular aspects is the flame scanner upgradations, the cold flow monitoring systems, and milling system automations, which is most crucial. If we automate the milling system, then the aberrations in taking mills, the more primary air or manual mode mill operations can lead to some sort of errors. And as you have, sir, you have rightly pointed out, the error is increasing at a lower load. So that sort of error can be minimized when we automate the entire system. So these are some of the interventions we can think for. Similarly, this is another areas where we have to optimize the number of milling systems. This is also crucial along with that flame scanner, where from say 7 mills to 6 mills, then 4 mills, then 3 mills. Sometimes operators are to some extent hesitant to come down to so much of lower optimizing the number of mills. But this is most crucial, and mill scheduler will dictate to come down to optimize the number of milling systems. Another point, the drum level fluctuations, where we have seen that our TDBT recirculation valves, which are on-off type, can lead to some problem with respect to drum levels. So we are replacing those valves with the modulating type, and of course, the loop tuning of drum levels are also can play a very crucial role here. The steaming of economizer, yes, economizer steaming is an issue, but we can optimize our sliding pressure operation to modified sliding pressure operations to avoid this type of steaming situations. But at the same time, as Mr. Chitora had pointed out, the provision of additional HP heater can be extremely helpful in managing this type of issues. Primary airflow is another areas where we come down to 40%, air will come down, and as a result, with the 2 fan operations, the one fan or both the fans can go into a stalling zone. So the solution in this case will be the automations again, where we can automate the system and come down to single fan operation, both FD and primary air, and to optimize primary and secondary at lower load. This is a typical ramp rate what we are nowadays pursuing, and in fact it is a step functions, as because we do not have milling system automation. So you have to take a ramp, then again take a pause for stabilizing the boiler and taking the mill into service, and again taking another ramp. So it is a step-by-step way we are moving, and now it is a mandate for all power generating units to follow 1% ramp. And in fact, the number of ramps coming are so much in some of our units, particularly at medium cost units and the units located at non-fitted stations. They are having a multiple number of ramps, maybe 10, 12 ramps in a day we are experiencing. And this type of ramping along with this temperature controller, smart controller, we cannot sustain, because all those ramps can lead to the temperature variations and a lot of aberrations in parameters. So,
Mr. Banerjee, please
yes,
speed it up.
yes.
Yeah.
So this is the one of the most important aspects where we can how we can move ahead. One is the training awareness. Another is the implementation of some of our experimentations in some of the modifications. And at the same time, we have to have a defense strategy. That defense strategy is just like turbine stress evaluator. We have to install the boiler fatigue monitoring system. We have to introduce the equivalent operating hours, as we have seen how this type of defense strategy can be adopted to minimize the impact. And this is the Dadri Unit 6 along the host of solutions. It is a basket of solutions, in fact. And from that, we have to select, and we have based on the unit specific, based on the equipment, based on the coal use, and based on our pilot study experience, we can select some of the solutions, and we have to implement that solutions. And these solutions is not the standard solutions. It will vary from station to station. This is Simadri experience, where we are introducing some of the advanced process control where steam temperature, unit response, and combustion optimizations are taking place. And in fact, we are implementing all those. So Dadri and Simadri experience are really is on. And in fact, what we think we can conclude here that with the experience of Dadri and Simadri, definitely we can come to some sort of conclusions how we should move ahead under this typical way of absorbing, integrating renewable power to the grid. Thank you, sir. Thank you so much.
Thank you, Mr. Banerjee. Very lucid presentation. I understand because of the the paucity of the time. I think this is for all the presenter that we could not cover. This is a very big subject, and of course, in your short presentation, you have been able to sensitize the entire audience on the how we should manage the flexible operation. There are many things to do because these are just started now. One question to my mind, I don't know who is going to answer, is this that you talked about the experimentation on 500 megawatt units, which is a subcritical unit. And so what is your experience with the supercritical and ultra supercritical units in India for this flexible operation? If you can quickly, someone, Snashish, if you can.
Yeah, can I answer that?
Yeah, please.
Sir, one of the basic objective in our mind as an organization, not in the sector specific, but as an organization, we believe that these supercritical units, which are having a very extremely high efficient, it is 2000, 2100 kilocalorie, but as because they are located at a remote areas or at areas which is away from coal mining areas, those units are under shutdown condition. This is a highly precarious situation. So we should not touch those units. There should be some methodology of running those units, and we should flexibilize the units which are 500 megawatt, because the 500 megawatt, if we flexibilize that, then quantum of flexibilization is possible with the 500, because as we come down, we can come down 500 to 200 megawatt. 300 megawatt of margin is available. And in case of 200, those units are older units. And as you can understand, sir, that this is the control methodology. As advanced control will be, it is much easier. So for 200 megawatt, it's extremely difficult to come down so much below, and at the same time with so much of higher ramp rate. So that is the reason why we are touching 500 megawatt. But in the days to come, definitely we have to touch those units also.
So we have to get the experience yet. I mean, you have to get. We have not got the experience of really, going for flexible operation in the for the the supercritical or the ultra supercritical units so far.
Got it.
Okay. So thank you very much. Is there any question and answer, Mr.
So there are 2-3 questions. I'll address them personally because we're running out of time. So request you to conclude the session. Ravi sir, we lost you. Sir, you can
Hello.
conclude the sir, you can conclude the session. Probably the questions we'll address them personally.
Thank you very much, all the speakers. Of, uh, yes, and for this thermal power plant flexible operations. And I think the work has started. NTPC and the many other private power stations shared the effort on a technical foot at how to manage this the operation. With this, thank you all for giving us this the flexible operation. Thank you. Can you hear me? Yeah.
Yes, sir.
We close this session? Right. Thank
Yeah.
you.
Thank you very much.
Thank
Goodbye.
you. Thank you. Bye
Bye.
bye.
Thank you. Bye-bye.